Hi everyone, welcome to TOC class. So we are seeing Turing machines, right? Okay. So this is the QR code of my compiler design textbook. If you have not bought it, please buy it from PW store. It will be helpful for BTech, MTech and GATE. Okay. And this is the QR code of my Telegram channel where you can do discussions. Okay. Now, in the last class, we were discussing about Turing machines. And in today's class also, we'll discuss about Turing machines. Okay. In today's class also we'll discuss about Turing machines. Okay, fine. So let's see Church-Turing thesis. Church-Turing thesis, right? So what does this say is every logically computable function is Turing computable. Turing computable. Right? Every logically recognizable function is Turing recognizable. These statements are important. Okay, we are not going to prove them because proof will be very complicated and proof will not be asked in exams. Hello Mohit, hello Mono, hello everyone, right? So Turing recognizable means recursively enumerable language, and Turing decidable means recursive language. Turing decidable means recursive language. Okay. Now let us see variations of Turing machine. Let us see variations of Turing machine. Now what are the various variations of Turing machine? So if you look at standard Turing machine, which is a deterministic Turing machine, standard Turing machine is nothing but deterministic Turing machine, right? So it will have a control unit. Control unit is nothing but finite automata kind of thing, plus read write tape. Control unit plus a tape on which you can read and write, and you can move right or you can move left. This is a standard Turing machine, and there is a single tape, and there is a single tape, right? Now I'll give you some modifications. You tell me whether these modifications, sir, I clear GATE 2025. Cyan Paul. Very good, Cyan. Try to revise all the subjects. You will be able to get a good rank in 2026. Okay. Very good that you cleared GATE 2025. Do well in GATE 2026 as well. Okay. Fine. So now let us see variations of Turing machines. Okay. So one variation is Turing machine with stay option. Turing machine with stay option, right? Which means Turing machine can move right, can move left, and also can stay. Sir got an NIT. So that's okay. Even NITs have very good placements. So I suggest that you join NIT, right, and continue. There will be not much difference between NITs and IITs. Placements will be almost the same and the salaries will be almost the same. So even if you get an NIT, just continue it, okay? And all the best for your placements, right? So I think you must have completed your first semester also. That's a nice thing, right? So do some practice of algorithm data structures. You will do well, okay? Practice some coding from now on, okay? Now answer this question. Turing machine with stay option. So stay option means stay option means the delta is going to be if you are in one state, and if you look at tape alphabet, you will go to some state, and you will write something on the tape, and then you can move left or move right or stay. You can move left, move right or stay, right? So even then when you add Turing machine with stay option, it is not going to have more power compared to standard Turing machine, right? So you can say it is of same power. You can say it is of same power. You can say it is of same power, right? Now there is one more variation. So like that we have 7 variations, okay? 7 variations. We will see all the 7, okay? So Turing machine with semi-infinite tape. Turing machine with semi-infinite tape. Turing machine with semi-infinite tape, right? So what is this Turing machine with semi-infinite tape is, generally when you look at a tape, there will be blanks both on the left side as well as on the right side, right? So in a general Turing machine, if you look at the tape, let us say AB is the input. Now there will be blanks to the left of it, infinite blanks, and there will be blanks to the right of it, and you can use all the blanks, right? There will be blanks to the left of it, there will be blanks to the right of it, and you can use all the blanks. Right? Now what do I mean by semi-infinite is, now AB, there will not be blanks on one side, there will be blanks on only one side, right? So this is semi-infinite tape, right? This is semi-infinite tape. Now even if the Turing machine has semi-infinite tape, it accepts the same language as standard Turing machine, right? So same language or same power as Turing machine. It will have same power as Turing machine. It will have same power as Turing machine. It will have same power as Turing machine, right? Right. Now, multi-tape Turing machine. You answer this. Multi-tape Turing machine, right? Now, if I give more tapes to Turing machine, what do you think is the power? If I give more tapes to the Turing machine, what do you think about the power? What do you think about the power? If we add more tapes to the Turing machine, what do you think is the power? Multi-tape Turing machine. Very good, Skanda. P. Skandap. Very good, Skanda. So, even if you add more tapes to a Turing machine, it will have the same power, right? So, what do I mean by multiple tapes is, now when you have a control unit for a Turing machine, generally for a standard Turing machine, there will be only one tape, right? But when you have multiple tapes, let us say this is tape 1, this is tape 2, this is tape 3, and let us say there are inputs and all of them. So multi-tape Turing machine means it can access different tapes. It can read write on different tapes. Even if you give it multi-tape, Turing machine will accept the same language. Turing machine will accept the same language, right? Therefore, it is going to be same power. It will accept the same languages. Therefore, it has the same power. Therefore, it has the same power as standard Turing machine. It has the same power as standard Turing machine. Okay. Okay. Now let us see offline Turing machine. Let us see offline Turing machine. So what does offline Turing machine mean? What does offline Turing machine mean? I will tell you what it means. You tell me whether it is of same power or not, right? So offline Turing machine means we read in one tape, we read in one tape, we read in one tape and write in a different tape. We read in one tape and write in a different. We read in one tape and write in a different type, right? So read write tapes are different. Read write tapes are different. Read write tapes are different, right? So what does this mean? It has two tapes. One is for reading and other is for writing, right? So it has two tapes. Turing machine has two tapes. Let us say this is the control unit, right? And it has two tapes. One is for reading and one is for writing. One is for reading and one is for writing. Read write tape. One is for reading and one is for writing, right? This is called offline Turing machine. And even if you have different tapes, it has same power as the standard Turing machine, right? it has same power as the standard Turing machine, right? So it has same power as standard Turing machine. It is not going to increase the power, right? Now let us see one more variation. Let us see one more variation. Let us see one more variation. Multi-dimensional Turing machine, right? So here the tape is going to be of multi-dimensional. Now if you look at a standard tape, standard Turing machine tape, it was one dimensional, right? It was like a one-dimensional array. It was like a one-dimensional array, right? Now when you see multi-dimensional Turing machine, there it will be like a two-dimensional array, right? So multi-dimensional Turing machine will have multiple dimensions. It will have multiple dimensions like this, okay? It can be of any dimensions, right? So now if you look at the transition function, a Turing machine in a particular state, will see tape symbol, and it will go to a particular state and it will write something on the tape, and now it can move either to the left or to the right or up or down, either left or right or up or down, which means if you are here you can move left or you can move right, you can move up or you can move down, right? Now do you think that this Turing machine has more power than standard Turing machine? Do you think that this Turing machine has more power than standard Turing machine? No, it has the same power as standard Turing machine, okay? It has the same power. It has the same power. It has the same power, right? It has the same power, right? Now let us say non-deterministic Turing machine. Non-deterministic Turing machine, right? Will a non-deterministic Turing machine have more power than deterministic standard Turing machine? No. In case of Turing machine, non-deterministic Turing machine and deterministic Turing machine both will have same power, right? So non-deterministic Turing machine is equal to in power deterministic Turing machine, right? So there are three kinds of machines and you have to remember about these three. So coming to finite automata, DFA is equivalent in power to NFA. DFA is equivalent in power to NFA, right? But then deterministic push-down automata is less powerful than non-deterministic push-down automata. And coming to Turing machines, deterministic Turing machines and non-deterministic Turing machines are equal in power, right? So what does this mean? Whatever languages are accepted by DFA will also be accepted by NFA, and whatever languages accepted by NFA will also be accepted by DFA, right? But what does this mean? This means that there are some languages which will be accepted by non-deterministic push-down automata but not by deterministic push-down automata, right? Now what does this mean? Any language accepted by non-deterministic Turing machine can be accepted by deterministic Turing machine also. So in case of Turing machines, both the Turing machines are equal in power. In case of Turing machines, both the Turing machines, deterministic and non-deterministic, are equal in power. equal in power, right? Now, the seventh modification is universal Turing machine. Universal Turing machine. Universal Turing machine, right? Now, what is universal Turing machine is? What is universal Turing machine is? Now, you can give the universal Turing machine some Turing machine as an input, okay? Binary encoding of some Turing machine as input. Binary encoding of some Turing machine as input, and it will have a current state of the Turing machine. Current state of the Turing machine, and then it will take the input in a separate tape. So it is going to have three tapes, okay? Separate tape, let us call it as input tape, okay? So universal Turing machine has three tapes. In one tape, it is going to take a Turing machine as an input, and in other tape, it will record the current state of the Turing machine, which is given as input, and in other state, it is going to take the input, and it is going to run this Turing machine on this input, right? It is like a reprogrammable computer. For example, if you give adder here, this Turing machine will act as a adder. If you give a power n, b power n, this Turing machine will act differently, right? So it is like a computer. Now, even universal Turing machine is same in power as standard Turing machine. It is same in power as standard Turing machine, right? Now let us see three more variations, okay? Let us see three more variations. Let us see three more variations, okay? Let us see three more variations, okay? 1 minute. Let us see three more variations. Now let us see three more variations. Let us see three more variations, okay? So first one is halting Turing machine. Halting Turing machine. So a Turing machine which halts on every string. If it accepts the string, it will halt in final state. If it doesn't accept the string, it will stop in non-final state, right? Anyway, for all the inputs, it is going to halt. It is not going to hang, right? Now, this Turing machine is less powerful than standard Turing machine, right? This Turing machine has less power compared to standard Turing machine. Standard Turing machine, right? So, halting Turing machine is less powerful than standard Turing machine, right? Now, standard Turing machine actually accepts all the recursively enumerable languages, and halting Turing machine actually accepts only recursive languages, okay? So halting Turing machine corresponds to recursive languages, and standard Turing machine corresponds to recursively enumerable languages. Recursively enumerable languages, okay? Recursively enumerable languages, right? And the next one is linear bounded automata. Next variation is linear bounded linear bounded automata, right? So what does linear bounded automata mean? The tape is not going to be infinite, right? So if you provide input, let us say A, B, C, now at the either sides of the input, there will be a limit. There will be a limit, right? Now you cannot cross this dollar. You cannot cross this dollar, which means you can only use the space provided to you for the input. You cannot cross the space provided to you for the input, right? Right? So now linear bounded automata is less powerful than halting Turing machine, and halting Turing machine is less powerful than standard Turing machine. Linear bounded automata is less powerful than halting Turing machine, and halting Turing machine is less powerful than standard Turing machine. Standard Turing machine, right? So linear bounded automata accepts context sensitive languages, and halting Turing machine accepts recursive languages, and standard Turing machine accepts recursively enumerable languages. Recursively enumerable languages. Okay. And then the next Turing machine is read only Turing machine. There will be no writing. Okay. Read only Turing machine. Read only Turing machine. Right. So what does it mean? It means Turing machine plus read. Turing machine plus read. It can only read from the tape, and it can move right or left. It can move right or left, right? So it is like a two-way finite automata. It is like a two-way finite automata, which is equivalent in power to a finite automata, right? So if a Turing machine cannot write, it is as good as a finite automata. It is not powerful than finite automata. It is not powerful than finite automata, right? Okay. And one-way Turing machine. And one-way Turing machine. And one-way Turing machine, right? So this is a finite automata plus read write head plus it can move either right or left. It cannot move in both the directions. It can move in only one direction, either right or left. This is called one-way Turing machine. This is called one-way Turing machine. This is as powerful as a finite automata. This is as powerful as a finite automata. As powerful as a finite automata, right? Right. So let us see recursive and recursively enumerable languages. Recursive and let us see recursive and recursively enumerable languages. Recursive and recursively enumerable languages, right? Let us see the definition. Let us see the definition. L is recursively enumerable if L is recursively enumerable if there exists a Turing machine accepting L. There exists a Turing machine accepting L. L is a recursively enumerable. L is recursively enumerable if there exists a Turing machine accepting L, right? And recursively enumerable languages are Turing recognizable languages. Turing recognizable languages. Recursively enumerable languages are Turing recognizable languages, right? And L is recursive if and only if L is recursive if and only if L is recursive if and only if there exists a halting Turing machine. If and only if there exists a halting Turing machine, right? So what can we say? Turing recognizable are equivalent to recursively enumerable and Turing decidable are equivalent to recursive languages, right? Now, if a language has Turing machine, but no halting Turing machine, then the language is recursively enumerable but not recursive, right? Then the language is recursively enumerable but not recursive. Okay, let's now see the properties. Let's now see the properties. Okay. So if you look at recursive and recursively enumerable languages, if we have recursive languages here, you will have recursively enumerable languages here, and you will have set of all languages here, 2 power sigma star, right? So 1 is called recursive, 2 is called recursively enumerable but not recursive, 3 is not recursive, right? So 1 is called recursive, and 1 plus 2 is called recursively enumerable, 1 plus 2 is called recursively enumerable, right? And 2 is called recursively enumerable but not recursive, and 3 is not recursively enumerable, right? And 3 is not recursively enumerable, right? Now let us see enumeration procedure. Now what is enumeration? Enumeration means listing, which means writing down all the strings of the language with a guarantee that every string in the language will occur after some number of steps. That is called enumeration procedure, right? Enumeration procedure. Okay. L is recursively enumerable. L is recursively enumerable if and only if L is recursively enumerable if and only if L has Turing enumeration procedure. L has Turing enumeration procedure. L has Turing enumeration procedure, right? So what do I mean by Turing enumeration procedure? We should be able to generate only members of the language. The non-members of the language may be generated or may not be generated, right? So recursively enumerable means, enumerable means Turing enumerable, right? So recursively enumerable languages means Turing enumerable. Recursively enumerable language means Turing enumerable. Turing enumerable, right? Now a set A is countable if and only if it has enumeration procedure, right? A set A is countable if and only if it has enumeration procedure. A set is countable if and only if it has enumeration procedure. A set is countable if and only if it has enumeration procedure. If and only if it has enumeration procedure, right? So you can divide sets into two types. One is uncountable and other is countable. One is uncountable and other is countable. One is uncountable and other is countable. Now, in uncountable, you can say that the language is uncountably infinite. The language is uncountably infinite. In countable, we can say that the language is countably infinite. The language is countably infinite, or the language is countably finite, or the language is countably finite. The language is countably infinite, or the language is countably finite, or the language is countably finite, right? Now, L is recursive. L is recursive. L is recursive if both L and L complement, have Turing enumerable procedure. Turing enumerable procedure. If both L and L complement have Turing enumerable procedure. Turing enumerable procedure. If both L and L complement have Turing enumerable procedure, right? So if some language is Turing enumerable, if some language is Turing enumerable, but its complement has no Turing, enumerable procedure, then the language is recursively enumerable but not recursive. Then the language is recursively enumerable but not recursive, right? And coming to membership algorithm, right? L is recursive if it has membership algorithm. Right? So what is the meaning of this? Which means if it has membership algorithm means it is going to halt on both members and non-members, right? So L is recursive if it has membership algorithm means it is going to halt on both members and non-members, right? But for recursively enumerable, it is not the case. It will halt on the members, but for non-members, it may halt or it may go into hang state. Right? And coming to lexicographical ordering, coming to lexicographical ordering, L is recursive if L can be enumerated in lexicographic order. If L can be enumerated in lexicographic order. Right? So what is lexicographic order? We will see it shortly. Right? And next one is closure. Closure property. closure property. So under union, intersection, concatenation and clean closure, both recursively enumerable and recursive languages are closed. Both recursively enumerable and recursive languages are closed, right? L is recursive if and only if L is recursive if and only if L complement is recursive. L is recursive if and only if L complement is recursive. L complement is recursive, right? L is recursively enumerable. L is recursively enumerable. It means that L complement may or may not be recursively enumerable. May or may not be recursively enumerable, right? So what are the various cases? So what are the various cases between recursive and recursively enumerable are? Let us say this is recursive, this is recursively enumerable, and let us say this is set of all languages. Now there are only three cases possible. If L1 is recursively recursive, then L1 complement is also recursive, right? Now if L2 is recursively enumerable but not recursive, then L2 complement is definitely not recursively enumerable, right? Or L3 can be non-recursively enumerable, then L3 complement will also be non-recursively enumerable, right? Only these three chances are possible, right? Therefore, if a language is recursively enumerable, let us say it is recursive. If a language is, every recursive language is recursively enumerable, right? So if a language is recursively enumerable, in case if it is recursive, then its complement is also recursively enumerable. If a language is recursively enumerable but not recursive, then its complement is not recursively enumerable, right? Or if a language is not recursively enumerable, then its complement is also not going to be recursively enumerable, right? We have these three cases. Only three cases are possible, right? Only three cases are possible. Okay? 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 Fine. So we will continue the remaining topics tomorrow. Okay? So we will end this session here. Thank you everyone. Good night. Thank you everyone and good night.